Everybody, welcome to Thursday, day number 4. Let's get started. You are in the Thursday plenary, and today is Rubin Research Spotlights. I will let our chairs tell you what that means. Oh, might be out of batteries. That's okay. I'll just use this. Okay. As a reminder, we have a code of conduct. If you experience or witness any violations of that code, there are people who are willing to be contacted about it, and they'll help you through it. Another reminder to wear a mask if you want to and respect other people's decisions, and to keep an eye out for those social battery pins. It is day 4. They might be getting low. As a reminder to our virtual participants, please stay muted if you're not speaking, and do post questions for our speakers in the Slack space. And when you do, it's helpful if you say whether you want to unmute to ask your question, whether you want to have it read out for you, or if you just want it answered in Slack. That helps our virtual moderators. One announcement for our virtual participants: last call to upload a photo of yourself participating virtually in the RCW to ls.st/RCW 2024 by noon today, please, because we want the picture done and ready to circulate tomorrow. Another announcement is that the LSST CAM Raft Tower Module Show and Tell is happening today in the SUSB lobby. That's where the posters and the other coffee and everything are. And you'll be able to come and see the LSST CAM sensors and the readout electronics up close, and ask your camera questions to 2 members of the camera team. Hannah and Travis will both be there. And I'm going to turn it over to Matt Wiesner and Pat Burchat, who are your hosts for this morning's plenary.
Thank you. So good morning. I'm Matt Wiesner, and with Pat Burchat would like to introduce the Research Spotlight Plenary on behalf of the Scientific Organizing Committee. The SOC invited 4 speakers doing meritorious Rubin-related research to give short talks on their work. We had planned for 2 in-person speakers and 2 remote talks. Due to flight issues, we'll be having 1 in-person speaker and 3 remote talks. Our first speaker is Louise Edwards. Louise Edwards is an associate professor in the physics department at California Polytechnic State University. She was previously a lecturer in the astronomy department at Yale University. She's especially interested in studying galaxies and clusters. Her talk is entitled Exploring Galaxies and Large Structures in Rubin DP 0.2, the BCG merger rate 1 gig a year ago.
Thank you. The largest galaxies in the local universe, brightest cluster galaxies, formed most of their stars and assembled a very long time ago. But even today, there's still a few that are actively assembling. This work is from this paper, Stellar Populations and Merger Rates of Brightest Cluster Galaxies, so BCGs, 1 billion years ago. And all of the co-authors are Cal Poly students who were undergraduates at the time of this work. Their beautiful faces are shown there. So we're going to focus on the largest, reddest, and deadest galaxies, brightest cluster galaxies. But presumably these galaxies, or at least their stars, were once young. So we want to know how, where, and when active, bright, star-forming galaxies became these red and dead, large, old galaxies that we typically find at the core of clusters. Now, at the core of galaxy clusters, there's a fair amount going on. So I want to bring up a couple of the issues so we can think about the how, where, and when with some detail. You probably know that galaxies themselves are formed as stars, gas, dust, and dark matter. Galaxy clusters as well, we think of as groups of galaxies and dark matter, and also lots of hot X-ray emitting hydrogen gas, right? Loose hydrogen gas that's bathes the entire cluster, that is so hot it emits at X-ray temperatures. And actually a large component of the baryonic material in clusters is in this hot hydrogen gas. But you're probably used to looking at galaxy clusters in the optical, more like this. This is Coma, a nearby galaxy cluster. And you can see with their eyes, there are two large, in this case, two very large galaxies, right? These big red, bright galaxies. And you can probably also notice there's some other smaller galaxies, red galaxies that seem to be, you know, you could imagine them buzzing around the main galaxy if this was a video. Now let me shrink this down and just show where that bright X-ray emitting gas is that I was talking about earlier. You can see it bathes, it permeates the entire cluster. And this material you could imagine might interact with like a galaxy that's falling into that cluster. So let's imagine a galaxy falling into this intra-cluster medium. In that interaction, you might imagine gas and dust, you know, getting ripped off, pressure stripped off of that galaxy. And you could imagine this galaxy interacting with other galaxies in the cluster, maybe even with the gravitational potential of the brightest cluster galaxy itself, and stars whipping off of those systems. So material stripping from galaxy, or galaxy BCG, or galaxy IC, intracluster medium, interaction settles in the gravitational potential well of the cluster eventually. So here's a Sloan image of a nearby galaxy cluster. And if you have Rubin, you'll see very, very deep in this, and you'll see something called the intracluster light. This image was taken by Kluge after about 24 hours of observation on about a 1 meter telescope. And what you can see here is faint and diffuse starlight, okay? Intracluster light, starlight, which is thought to be a fossil record of cluster dynamics. It has its own chemical signature. The outer ring of this graphic is showing you that it's got more young metal poor populations than the inner ring, which is the core of the brightest cluster galaxy, which is dominated by very old metal rich populations. So the intracluster light's quite different. Also kinematically, the stars are associated with the cluster and not the BCG. But when you look at it, it looks like an extension of the BCG. So it can be important when trying to figure out the evolution of a brightest cluster galaxy and this intracluster light, to think of them or study them in tandem, to think about the BCG and the ICL together. So most BCGs in the local universe, or many of them, look like in the top graphic there, very smooth, very large, diffuse on the outskirts. And as I said at the intro, most BCGs likely assembled around redshift 1, sort of in a two-phase process. Above redshift 1, generally through building their mass through star formation, and then gradually moving to a phase of dry merging. But a small fraction of brightest cluster galaxies seem to still be merging today, have double cores in their nuclei, or lots of other galaxies nearby that are roughly the same magnitude that you could imagine would merge to form a larger system soon. So in this, we identify and characterize the galaxies that are expected to merge or interact with the BCG. We determine the number and mass of these close companions. So potential major mergers, that means that the mass or light ratio between the main BCG and its close companion is within a 4:1 ratio. And potential minor merging, so 20:1 ratio galaxies. And we think this will help us our understanding of brightest cluster galaxy and ICL formation. Because those interactions, those stars are either going to go into the brightest cluster galaxy or into the intercluster light. So we take 88 brightest cluster galaxies from the SDSS MANGA survey. So MANGA is an instrument That's an integral field spectrometer, so you get a spectrum for many regions inside the field of view. This is great for us because we can get a spectrum of the brightest cluster galaxy and also all these close companions. And then with DP0, we go and find 123 other brightest cluster galaxies that have the same redshift distribution, color, magnitude distribution. And we look at the object catalogs, so the simulated sky, and we also have the truth catalogs, right? So also the underlying, is this really a star or galaxy? What is the redshift? And we'll use the DP0 to help us understand the reliability of our studies with MANGA. So I have a quick game with someone beside you. You can decide which is the DP0 cluster core and which is the SDSS actual sky cluster. You have 2 seconds. Which one is which and why? Okay, so this is the real sky. You might notice it's a little noisy. This is excellent SDSS data. And you also, maybe you got this clue of that's the footprint of the MANGA instrument. So our process is we count the number of close companions per BCG. We estimate the merging probability of those galaxies. We estimate the merging time of those nearby neighbors, and then we assess the reliability, and that's where DP0 comes in. So these are our results. So what we do is we count and see the number of companions per BCG at different radii. So here I've illustrated out at a projected 10 kiloparsec radius from the BCG, and then we do 20, we do 25, we do 30 kiloparsecs away from the BCG. And what you notice is there are very few 4-to-1 companions per BCG, right? Those numbers are very low of companions per BCG. This is in the local universe, and as we expect, most BCGs are already well formed. But there are significantly more potential minor mergers, so those are the blue dots. So one of the arguments we're trying to put forth is, what is the importance of minor merging to changing the shape, the structure, and the mass of BCGs, even in the local universe? So there's significantly more potential minor mergers. The lines now are the data from the DP0 truth catalogs, okay? Black are the 4-to-1 potential major mergers, and blue are the potential minor mergers. And you can see the black dots in the line fit well. That's great. So we are happy the 4-to-1 companions compare well to the DP0.2 simulated data set. But we may be overcounting the 20-to-1 companions. I think there's a few reasons for that. A lot of it's probably projection effects. When we go in and look at the spectra of the low mass companions, those are pretty ratty spectra. So we probably were overly optimistic. Also, there may be classification issues. If you have a very faint object, it could be classified as a galaxy, maybe it's a star. And finally, I think that the BCG itself might be polluting the data from the lower mass galaxies. So these are my conclusions. 4-to-1 yay, 20-to-1 caution. I want to point out the result, the title of this talk. The merger rate, we calculate the merger rate as 0.08 mergers per gigayear for a galaxy in the local universe at this redshift. And if you take an average mass of the companions, this leads to a potential growth by about 2.3% per gigayear. For the 20-to-1 companions, so this is where we have lower mass companions, but in a hierarchical universe, right, we expect many, many more of these. So can we actually add significant mass just because there's so many of these little guys? Our results give a merger rate of 0.26 per gigayear, and that could increase the mass by up to about 3.5% per gigayear. These are low numbers, both of them, but if you look at them, you can see that potentially the low mass companions could be adding comparatively significant mass at these redshifts. But of course, we want to be cautioned, this is probably an overestimate. I want to point out the really amazing work by Sarah Bruff and her group. This is from Banks 2021. They did a similar study with many more galaxies. They have much tighter error bars, and we are consistent with that. I want to point out studies at different redshift ranges. So I worked with Dave Patton a few years ago, which is actually like a decade ago. We looked at a sample at redshift of 0.3. Those are the red squares, and you can see they have higher numbers of companions, right? So earlier on in the universe, there was more of this merging activity going on. So the merger rates are dropping, have been dropping since redshift 1 when we go into the literature and collect sort of what's been done so far. So I want to end by saying a small fraction of BCGs locally are still building. Minor mergers could add significant mass compared to major mergers, but the number of close companions may be overestimated. And what's really exciting about Rubin is it's going to go really deep. So if we take the time to properly calibrate these projection issues, we could potentially be looking at really low ratios, really low minor mergers, which I think will be exciting. Thank you.
Thank you. I may have missed it, but how did you calculate the merger timescale?
Okay, I didn't say, but there are two ways that we do it. We look at the dynamical friction timescale, which is up here on the left. So the important components here are how far away the satellite is from the BCG, and also the velocity of the companion as well, which we estimate from the redshift difference, and the mass of that satellite. We also use this other merging timescale, which is actually calibrated from the Millennium simulations and popular in this work. A lot of people use this calibrated way, which depends on the mass of the companion and again, how far away the companion is. So one of these is basically like gravity dynamics, and the other one is calibrated from simulations.
So you were comparing manga data or SDSS imaging data with the DP 0.2. They're quite different depths. And how do you calibrate? In order to make those comparisons, you have to understand the relative depths. Can you say a little bit more about that?
Yeah, I'm using the manga spectroscopic data, right? Yes. So, and they are at quite different depths. Absolutely. So actually, most of the close companions that we find most of the close companions that we find are really low mass, or more than 20, not most, but a lot of the close companions that we find are lower than 20-to-1 ratios. So what we do is that's why our error bars are so big. So we just make cuts where we're complete. And that's why I had all those different dots, essentially at 10 kiloparsecs where everything is complete. We actually have 88 BCGs, at 20, at 30, at 40. Or I think I stop at 30 here. Yeah, absolutely. Yeah. So when we choose our DP0 BCGs, we select them the same way to follow what our manga galaxies look like. And then when we look at the companions, we only look at complete depths.
Our next speaker is Jamie Robinson. Jamie Robinson is a postdoctoral research associate in the Institute for Astronomy at the University of Edinburgh. He completed his PhD at Queen's University Belfast. He is primarily interested in solar system object science. He will present the talk Solar System Alerts in year 1 of LSST.
Hi everyone, thanks very much for the invitation to speak. I'm Jamie Robinson, and today I'd like to talk to you about recent work I've been doing, which is looking into the effects of template generation on solar system science during year 1 of the LSST survey. So I'd just like to start by reminding us of some of the reasons why LSST will be a really excellent survey for solar system science. So the depth and coverage of LSST is expected to provide an order of magnitude increase in known solar system objects across all the major dynamical populations. So that's shown here in this table, showing the number of currently known objects and the number of expected LSST discoveries. Over the 10-year survey, we expect to obtain hundreds of detections for most of these objects, and these detections will be spread across 6 filters. So this will really help enable us to determine the physical properties of these asteroids and comets by analyzing their phase curves, their light curves, and their colors. But a really cool, important feature of LSST is that these transient detections will be made public within 60 seconds of the shutter closing. So these rapid alerts will provide excellent opportunities for follow-up observations of the most interesting objects. So for solar system science, some of the objects that would benefit most from rapid follow-up include interstellar objects. These objects have a very limited observation window within which to characterize them. Near-Earth objects, which are some of the smallest observed asteroids, and these also present an impact hazard to Earth. And also active objects which can undergo rapid changes in brightness and morphology due to mass loss via either volatile ice sublimation, rotational changes, or collisions. So just as a very brief aside from the templates I want to talk to you about today, I also want to mention some work that I've been doing detecting activity in solar system objects. And this work is part of a LSST UK in-kind contribution from University of Edinburgh and Queen's University Belfast. But essentially, LSST alerts are already going to provide some measurements of activity in a given detection. That's going to be based on the extendedness or trailing of a source and also its predicted magnitude. But to complement this, we are developing the Adler package, which contains additional tools to investigate the presence of activity in more detail. So we want to apply more sophisticated phase curve models, for example, and this will help improve the detection of photometric outliers. So for example, in this figure, if we have an expected phase curve behavior, we want to reliably identify brightness increases due to activity. And to do this, we want to use rotational likelihood phase curve models from Schemmel and Brown, or there's also some really interesting models coming from Carey et al. 2024. But we also plan to analyze the alert cutout images using methods such as wedge photometry, such as displayed in this figure here, or noise chisel image segmentation. But getting back to thinking about the generation of templates, the Rubin prompt processing pipeline will obtain transient detections from difference imaging. So this means that every visit needs its area of sky to have an existing static sky template image in the same filter at that time of processing. Otherwise, no detections can be made and alerts cannot be issued. So we expect that this will have quite a large impact on the discovery of solar system objects which are moving across the sky. And that's because the solar system pipeline will need nightly pairs of detections spread over a couple of weeks to correctly identify these real moving objects, and that's shown in this figure here. One thing that's really important to point out right at the start is that although although we may not get the alerts, the detections from visits without the alerts are not lost, because all these images will be reprocessed during subsequent data releases. But what we do lose is that like rapid nature of the alerts and the opportunity to follow up, which is really important for the transients such as interstellar objects and near Earth objects and active objects that I just described. So as such, we have built a framework to simulate the effects of template generation, which is something that has not yet really been fully accounted for in the analysis of like the science results we expect during year 1 of the survey. So we made use of the Rubin metric analysis framework, and we had some starting notebooks from the development team. And what we did is we considered template generation across a heel pixel representation of the sky, and heel pixels are just a method of dividing the sky into cells, essentially. But we decided to use heel pixels with similar sizes to the LSST CCDs, and also to the patches which the pipeline uses to represent the sky, and that's sort of demonstrated in this figure of the constituent patches and tracts for the pipeline. And what we did is then we investigated generating templates over timescales of days to weeks, because it's currently unclear like what will be reasonable to expect from Rubin during year 1. But for every single each heel pixel, we considered all of its visits in a given filter up to a given night Tn, where the previous night on which templates were made is Tn minus 1. If that template had at least 4 observations of sufficient quality on night Tn minus 1, we just quickly show our template image requirements here to do with seeing and depth. But we essentially then determined if that heel pixel had a template made, and if it did, all the subsequent visits to that heel pixel between Tn minus 1 and Tn could have generated alerts. So we then repeated this process, stepping through all possible TNs in year 1, and we recorded metrics such as the number of visits with alerts and the template coverage of each visit at the heel pixel scale. So we generated lots of results for different template timescales and filters, but here we're just quickly showing some heel pixel sky maps, and these show the number of visits at the end of year 1 for observations in the R filter. So on the left we have the baseline survey, and this assumed that templates already existed and alerts could flow from night 1, whereas on the right we have our simulation where templates were being generated every 7 days. So from the color bars, we can already see that template generation leads to a reduced number of visits across the whole sky, and that the coverage is actually patchier than the baseline for the template generation simulation. And then because we had considered template coverage at the heel pixel level, we were then able to record the number of heel pixels within each visit that had a template. Because due to like dithers and rotations in the survey cadence schedule, we would expect that revisits to the same field do not always align with the previous visits, and so that the coverage may not be completely even. So what this histogram is showing is the distribution of visit template coverage at the end of year 1. And we can see that most visits have either no coverage at all, and these are visits that were then probably incorporated into building templates, or the visits most likely have greater than 90% template coverage, and these are the visits that are likely to produce alerts. So then if we only select those visits with greater than 90% coverage, and we can pass these then to existing metric analysis framework solar system object metrics, here we've focused on the predicted number of discoveries. What we see is that discoveries are greatly reduced for all of the simulated dynamical populations, and that's shown in this figure here, which is for each different template generation timescale we tested, we compared the number of discovered objects in each population to the expected baseline. And what are particularly strongly affected are the main belt asteroids. They seem to lose about 50% of their expected year 1 discoveries, as shown here. But we can look a bit closer at how these discoveries are sort of coming in over time in this figure here. This is the cumulative number of discoveries, where blue line is the baseline, and then the colored lines are the different timescales. For, in this case, we're just focusing on the main belt asteroids. And we can see that the template generation introduces this delay of approximately 70 days before discoveries start to flow. And this 70 days is a combination of the time required to get template coverage across that area of the sky, plus the time taken to build those discovery tracklets that are required for solar system objects. And then one of the important findings of our results is that the visits and filters that already have lower levels of coverage in year one, these are the ones that are most severely impacted by template generation. So this is particularly evident for the U and G filters. So in this figure here, we're plotting the fraction of the expected baseline area that each filter is reaching as a function of time. So by the end of year one, the U and G filters are really lagging far behind all of the other filters in terms of template coverage. So this will be particularly important for any astrophysical transients which need color measurements using one of those filters. Likewise, there will be areas of the sky in the survey footprint that already have lower numbers of visits, and these are also strongly affected by template generation. So in this example here, we've considered a sample region of the North Ecliptic Spur, which will contain many main belt asteroids. So in the first panel here, we just showed the baseline and the expected LSST camera footprint. This is the template generation for 7 days, and we can see it's reduced in number and patchier. And then this is emphasized by this this image down here, number 3, which shows the difference between these other two. So it shows that we are losing visits across this region of the sky. But essentially, to conclude, I'd just like to really emphasize that, you know, this whole aspect of template generation in year one is relevant to like any science case that requires real-time alerts, not just the solar system objects that we focused on here. We found that, you know, there's possible benefits to generating template images as soon as they're available, provided those images meet our certain like image quality requirements. And then one of the things that we really want to think about is it might be worthwhile considering any small changes to survey cadence that could be made during year one in order to improve the generation of these alerts. But any changes, of course, would require additional cadence simulations to be produced so that we would avoid assess if it's worth doing or not and avoid negatively impacting the full survey's science goals. But this work is pretty much nearly finished being written up, so I've got a little QR code here for the overleaf paper draft if anyone wants to take a look. Or feel free to join the Slack channel at the LSST Slack if you want to discuss any further. But thanks for listening. I'll take any questions.
Hi, Jamie. This is Mario Urge. Thank you for doing this. This is fantastic. It puts some numbers on some things that we were thinking about and wondering about for a while. I have just one question about your plot showing the reduction for different populations. So when I typically think of main belt asteroids, I typically think of them as the easiest thing to find, and here they get hurt the most. Is there an intuitive way to understand this difference between different groups? Why are MBAs affected so much? And I can't tell what the top line is, but why is, for example, that population isn't?
Yeah, so to answer the first part of your question, I think the main reason why main belt asteroids are so badly affected is it's related to this. The North Ecliptic Spur, where a large number of these MBAs are going to be detected, is getting very patchy once you've introduced this template generation. And then it's related to probably the answer to your second part of the question. These objects up here are the TNOs and the more distant Oort cloud comets. And they're actually sort of okay compared to all the other populations. And we think that's because TNOs especially, they don't move very far across the sky over the course of, you know, this discovery time period. So basically, if you detect it at one time, it's still in an area that has templates most likely whenever you come back to it to build the tracklets. Whereas the main belt asteroids, I think, are starting to move at faster speeds where it may move from an area that has a patch to an area that doesn't have a patch. is my intuition on it, at least.
Perfect, thanks.
Hi, Jamie. It's Henry. Nice talk. Since you talked about it at the very beginning and then didn't touch on it again, do you have thoughts on how activity detection will be affected by using incremental templates, or no effect really?
Yeah, so to be honest, yeah, we didn't really focus much on like actual activity, because at the end of the day, you know, it doesn't matter if an object is active or not. If it doesn't have, if it's not discovered by its alerts, you won't get any activity information on it anyway. So I think it's like we've taken a step back and are addressing primarily just these objects need to be discovered in order to be characterized. I think. I hope that answers your comment question.
Yeah, I guess I'm just wondering, like, if the templates are like lower quality than like the final templates, whether you've looked into that at all, or
yeah,
that's, like,
so actually
way down the line or something.
That is a really good point as well, actually, because we have if I go back, I only briefly mentioned it, but like we've got very broad quality control requirements just based on like simple seeing and depth. And we're not even setting like a hard threshold. We're just setting build templates out of similar images. So yeah, template quality could be poorer in our simulations, but we did look briefly into this, where when we generated templates, we recorded metrics such as the mean depth and the mean seeing of the images used to build templates, and they're comparable to the overall year one statistics. So it's not like we're always building templates with really bad images, but you're 100% correct, where it's like this is the balance that you need to strike when considering when to build templates. Is the template going to be good enough to enable all of your science cases, or just good enough to maybe detect a couple of objects?
Great, thanks.
Let's thank Jamie again. Our third speaker is Ashley Villar. Ashley is an assistant professor of astronomy at Harvard University. She was previously the inaugural Mercedes Richards Career Development Professor at Penn State. She's particularly interested in using data-driven methods and machine learning to study the eruptions, mergers, and explosions of stars. She will be presenting the talk searching for astronomical anomalies in the cosmos.
Okay, great. Thank you so much. I hope you can hear me in the room, and I'll speak assuming you can. Again, I'm so sorry I'm not there. I was cyber stricken and stuck. So I will be presenting remotely, and I also have too many slides, so I will try to go a little fast. So in many ways, this is just an update on development that my group and many other groups are very actively working on to think about new ways of searching for really interesting transients in LSST. So why are we doing this? First, I just want to say by these transients, I mean really anything that's varying on a pretty wide dynamic range of timescales and luminosities. So as we all know, LSST will get 10 million alerts per night. Within that, it's kind of wild. There's going to be, as I'll show you, a few thousand supernovae every night. We expect something like 10 million AGN to eventually be discovered. Maybe like a dozen, I hope, kilonovae will be discovered, and millions, about 100 million again, of variable stars. There's really just so much going on, and none of that comes, unfortunately, labeled with that physics. And so it's really our job to figure out, well, what's going on and what's kind of the most interesting, whatever that might mean, to follow up in real time. My group thinks a lot about quark collapse supernovae. And as I mentioned, Vera Rubin is going to be really exciting for this field. So I'm showing you here just the discovery rate of supernovae as a function of year on a log scale. That's in the blue. And the point of this is just to say, one, we find a ton of supernovae every year right now, about 10 to 20,000, depending on what you call a supernova or a likely supernova. Vera Rubin is just going to blow this out of the water, and it's going to discover something like 1 million supernovae every single year. You know, of course, with that increase, we don't quite have an LSST of spectroscopy, although there's some really wonderful efforts underway. So only like 1% can actually be followed in real time, as in I get a spectrum. To me, the problem's a bit worse than this, in the sense of we're really limited, not just by our resources observationally, so I mean beyond spectroscopy, we're very limited in X-ray and radio follow-up, but really more importantly, our most valuable resource is human hours. We can't realistically, in my opinion, I think the field can't research in great detail more than probably like 100 events every year. So this really is a very small fraction of the events available to us. It's about 1 in every 10,000. And I always like to emphasize this point. It's literally like the supernova field got together and said, okay, guys, 2024, what are we studying? What's the one thing we're going to publish on? It really is an interesting question of what does it mean to be that important? I have a very biased view. I think that because we have this opportunity to find these 1 in 1 million level of interest, that we should really be looking for the weirdest of the weird, either new astrophysics or incredibly rare combinations of known astrophysics that really push our models of massive stars and their depths to their absolute limits as a way to ground these models in these extremities. So that is all to just motivate this idea that we are building new tools and methodologies to do really data-driven searches for new and interesting phenomena. The way that we've been going about this for quite a few years now is to turn to deep learning methods. It just means that we build neural nets, which are just like glorified linear algebra with a tiny little bit of nonlinearity stuck in there. And in particular, I work a ton in this field called representation learning, which is what it sounds like. We have these messy, ugly, well, beautiful data products that are these light curves. So time series are irregularly sampled and they're noisy, and they all come in different shapes and sizes. So that's our kind of initial data product. But in order to play with millions of these things, we need to take all of those light curves and kind of put them into the same tiny space. We need to map them out against each other so I can ask questions like, does this guy look similar to this guy or more similar to this guy? To phrase that in a more mathematical way, we're trying to take these kind of arbitrarily sized but large data vectors and turn them into some small low-dimensional fixed size vector space. The way that we've been going about doing this in a very data-driven fashion, because we don't know what physics we're looking for, is to use something called autoencoders. And there, all we're doing is we're basically asking a neural net, hey, can you look at this light curve and then like try your very best to just give me back the same light curve? The trick in doing this, though, is we say, while you give me back what I gave you, so here's my original light curve, I want you to squeeze that information down first and compress it into a really tiny vector. That vector needs to have everything it needs to fully describe back the original light curve. I'm going to give you flexibility, in that squishing and to kind of unsquish it, but I really, really, really care about this tiny vector space that you squish all of the supernovae into. So that's how the autoencoder works. His goal in life, that's all I like to say, the objective function is just, hey, recreate the light curve the best you can. We have lots of bells and whistles on this because the data has interesting properties. I'm not going to talk that much about it, just to say that, let's see. Because these things happen in real time, we make sure that we have things like recurrent neural nets, which just means that that vector is going to update whenever we get new data. And so that we can say, oh, wait, actually, at first I thought this would be the representation, but I got some more information and I think this will be the new representation. That's super important because it means that we can do things like search for anomalies in real time. And as new information comes in, we can change whether or not we think you look weird. And in fact, this is now old news. We did this for a really wonderful community simulation set called Plastic, and there's a new version called Elastic, where we had the answer. We had the back of the book answer the whole time, and so we could say, okay, take all of our supernovae, stick them into this low-dimensional space, this little scatter plot. So all those points are different supernovae. And then luckily, like I also know the type of each supernova, so I can check and see, hey, these things that look really, really far away from everything else in this space, are these actually rare physics? And it turns out the answer was yes, which is really cool. So taking a step back, this is just to say, what we've shown is that you can use these autoencoders to take those messy data, put them into a nice low-dimensional space like this, essentially, in a programmatic way, make these types of scatter plots and just say, oh man, you like are nowhere near where everyone else is. You must be a weirdo. And it does turn out that those weirdos correspond to rare physics. I also want to note, though, the thing that we've been focusing on most recently is thinking more broadly about the data products LSST gives us. In particular, for the thing I care about, supernovae, they happen in other galaxies. And actually, that picture of a galaxy tells you a lot about the supernova. It turns out that if you're from a weird home, you probably are also kind of weird physics. And so most recently, we have been training super similar autoencoders to do basically the same thing with galaxy images, but like with a few more bells and whistles. So instead of just saying, hey, here's a picture of a galaxy, squish it down and then unsquish it, we also say, oh, by the way, this first dimension of that squish space, the latent space, that should correspond to mass of the galaxy. Second dimension should be redshift. Third dimension should be star formation rate. And like, I'll give you a little bit of wiggle room, do whatever you want with the last dimension. Probably it should involve morphology though, but I don't have a good metric for that. And then we do a tiny thing to make sure that space is continuous. I think I'm lying and I'm not really going to come back to this. I don't have time. Okay. What's cool is that when you do this type of method, you can do things like really rapid inference on galaxy properties from the image alone. So here I'm just showing you, ignore the red and green, just look at the blue. I'm showing you the difference between the true parameters like the redshift and our inferred parameters. What's also really cool though, is that you can explore this low dimensional space and actually kind of generate new galaxies. You can really ask like what every dimension is doing. So I'm showing you, I'm just going to highlight row 2. I'm showing you, for example, holding all other dimensions of the space fixed. What happens when I kind of vary the dimension that's supposed to correspond to redshift? Well, at low redshift, I have a blob in this particular random set of parameters. And as I dial up redshift, it does kind of do what I expect. It gets smaller, and I don't know if you can see it, but it gets redder too. And then what's helpful is that in that free dimension where we said, like, do whatever you want, you can see that as I dial through that dimension, I have some weird morphology stuff happening. I go from kind of this central blob to maybe a disky type thing. The reason why we did this is because now we have a secondary latent space in which we can ask questions like, hey, where are the weirdos? Where are the things that don't look like anything else? Alex did, yes, thank you. Alex Gagliano is a postdoc I work with who did a really excellent job on this paper. And here we're just showing you examples of 2 kind of weird classes, these green peas and these red spirals. Don't ask me about them because I am not a galaxy person. I'll go so fast through the end. I want to quickly highlight the work of recently graduated student Patrick Aleo from UIUC, working with Gautam Narayan, who has worked to make this really awesome pipeline for the Young Supernova Experiment collaboration that combines galaxy images and supernova light curves into one space. And so we can ask for both of these properties at the same time, who's the weirdest one of all? We do find some really cool guys that I'm going to go kind of quickly. An interesting supernova we found through this is a type 1b, so that just means that he has a helium shell, but he has this very interesting, very long rise that indicative of circumstellar material, probably. If you look in the galaxy side of things, we find these really fun supernovae. This is really hard to see, but they're in these interesting ring galaxies. And then we've been working a lot to really understand how we can have a human in the loop in these processes. So for example, for LACE, this galaxy plus light curve anomaly detection algorithm, we actually get a Slack bot update every day at 9 a.m. That we can upvote and downvote to basically say, oh yeah, this is anomalous, this is interesting, that we will soon use to retrain the bot and get better with time. I'll skip this. Lace can do joint embedding, so we can do really interesting searches. Given one event that we've seen one time, we can ask, what's the closest looking event that looks similar to this? That's what I'm trying to show you here. But I really just want to show you my last slide. One of the things I've been so excited about recently is putting this kind of mind mapping idea, so building this low dimensional space that we can search and stuff together with a front end. Instead of having kind of complex SQL queries we have to build up, what we're thinking a lot about is building large language models that lets you directly talk to the data and kind of have the data talk back to you. So that when I'm looking for anomalies, if I maybe, well, this is pie in the sky, to be clear. I think in a wonderful world, what I imagine is that I'm someone who doesn't have all of the expertise to make some of these complicated machine learning algorithms, but like I can describe the physics I'm looking for. And I think our ultimate goal is to see if we can talk to our data in that natural language and to query that data to find the physics we're interested in. Okay, so I will stop there, and I think I have like 1 minute for questions.
Are there questions for Ashley?
I see Miriam's hand, but
we have one from
Thanks a lot for the talk. I just wanted to ask about the framework when you have both the galaxy images and the supernovae.
Yeah.
Are you using, or like at least training on galaxies for which you have the spectra for? Because otherwise it looks like you solve PhotoZ, and I just wanted to clarify.
Can you say the last thing? You solve what?
PhotoZ, like because you were showing.
No, okay. Or maybe I don't understand. I'm so sorry. It's possible I don't understand your question. For this project, we do train for galaxies where we do have, this is like the DECAL's survey, I think, for this one. And we do have spectroscopic redshift for this, but we are just using images to do the redshift inference.
We have a question on Zoom. If you could
Hey,
unmute and ask. Go ahead.
Hey, both our flights got canceled. So thanks so much for this wonderful talk. So one question I had was, when you ran your anomaly detection algorithm on plastic and then also elastic, right? They, as we've discussed before, they had a certain training set.
Totally.
So were you recovering the kind of weird supernova that we keep, having new types for?
Totally, yeah.
Or would inject it, because then obviously with training sets, what you get out is, depends on what you put in.
Totally. Yeah, it's a really good question. I should be super clear that I have not run this on Elastic, which has a lot more like included explicitly anomalous transients. Like, so for example, I think this is public. It has like a Dyson sphere, which is wild. And so I don't know if we can find that. For this work, for the anomaly detection work in plastic, we showed that the rarer classes would get higher anomaly detection scores. There are still some the newer classes you're talking about, like 1BNs or like 1CNs, I'm pretty scared. I don't think my anomaly detection algorithm I've shown here would flag them because they kind of look normal to me in the light curve. And so I don't know how they'll perform. I think it's a really good question though.
Let's thank Ashley again. Our final speaker is Nikki Arendse. Nikki is a postdoctoral researcher at Stockholm University. She completed her PhD at the University of Copenhagen. She's particularly interested in using gravitationally lensed supernovae to constrain the present-day expansion rate of the universe. And she will present her talk entitled Detecting Strongly Lensed Supernovae with LSST.
Thank you so much, Matt. And hello, everyone. I wish I could be there in person. But I think my talk follows actually perfectly after Ashley's one, because I will also talk about weird transients. And in this case, these are lensed supernovae. So we have a supernova and a lensed galaxy or cluster, and that results in a gravitationally lensed supernova. So here we see supernova Requiem, where these 3 light dots are all images of the same supernova. So how does this work? So here we have the setup. We have an observer and then a distant supernova explosion, and located along the line of sight is a galaxy or galaxy cluster that acts like a lens. So light from the supernova is bent and magnified by the gravitational potential of the lens galaxy, and it goes in multiple directions around the lens galaxy such that we see multiple images of the same supernova. And another important thing is that these images will not appear simultaneously to us because the light travels a different path. So we will also see a time delay between the appearance of the multiple images. And this quantity is crucial if we want to determine the expansion rate of the universe. So another thing we need for that is also the gravitational potential of the lens galaxy. And when we add those 2 things together, we are able to constrain the time delay distance, which is a ratio of distances between the observer, the lens, and the supernova. And this is an absolute distance, so we can use it to constrain the present-day expansion rate of the universe, or the Hubble constant. And there's a tension in this value, so independent measurements are very important. Okay, so lens supernovae are extremely useful, but they're also very rare because you need to have this exact alignment of the supernova, the lens, and the observer. And of course, supernovae also fade away over time. So it's very difficult to catch them, but we have found a few. So these are the lens supernovae that we found so far, for which we have the redshift of the supernova and the time delay between the images. And you see that the properties really range from, for the time delay, it's from a few hours to a few decades. So quite a big spread. And you also see 2 populations in this plot. So we have the blue ones, which are supernovae that are lensed by whole galaxy clusters. And then the red ones, which are supernovae lensed by single isolated galaxies. And the cluster scale lens supernovae have all been discovered with space-based telescopes, which is looking at a galaxy cluster and then discovering a new supernova in there. And these ones have larger time delays, so they're also quite useful for constraining the Hubble constant. Now we already have 2 measurements from lens supernovae of the Hubble constant. The first one from supernova Refstal, which gave a lower value of the Hubble constant, and then supernova Hope, which gave a higher value. So we haven't really solved the Hubble tension yet, but we're working on it. And the main uncertainties for both of these measurements come from the modeling of the lens modeling of the galaxy cluster, because there's so many different galaxies, so you have a lot of different components, and it's quite complex. That's why we would also like to use the galaxy scale lens supernovae, because there you only have 1 galaxy. But the problem with these 2 that we discovered so far is that both of them are super magnified and also have extremely short time delays, of the order of a day or even less for Supernova's Wiki. And these are both found by ground-based surveys, but these surveys that we have nowadays cannot look very deep. So you're really only reaching the top of the iceberg of the lens supernova population. And those are these really highly magnified ones. So what you really want is a survey telescope that can look much deeper into the universe, which is of course what we will get with the Vera Rubin Observatory. So this way, we will be able to see many more lens supernovae, and we're also more sensitive to the redder bands. So that's great. And initial estimates for the Rubin Observatory for how many lens supernovae will be discovered were of several hundreds a year, which is completely wild. And that also prompted us to start this project, which was from the Dark Energy Science Collaboration, where we took the exact observing strategy from LSST, from simulations, and calculated how many lensed type 1a supernovae we expect to find and what their properties are. So to do this, we simulated lensed type 1a supernovae, also including microlensing. So these are additional lensing effects from stars in the lens galaxy that give you additional magnification. Then we computed the light curves and combined that with the simulated cadence and observing strategy from LSST, so that for each object, we drew a cadence, and then we saw whether the lens supernova was detectable or not. So what do I mean by detectable? Well, for this, we use two criteria. The first one is the magnification method, where we look for lens supernovae that are brighter than a typical type 1a supernova at the lens redshift. And the second one is the image multiplicity method, because for some objects, if the distance between the images is large enough, LSST will actually be able to see different point sources. So that's the image multiplicity method. And combining both of these methods, so let's see what we found for the predicted lens type 1a supernova rate per year. In our simulations, we found that we should be able to detect 44 a year, which is also great. It's almost 1 a week, so it's really a lot compared to the sample we have right now. And of course, not all of those will be useful for cosmology. Some will have very short time delays still. But if we look at the ones with time delays larger than 10 days, we still expect to find around 26, which is really great. Then we also looked at the deep drilling fields, which are parts of the LSST footprint that will have a higher cadence and larger depth. So it would be great to discover lens supernovae in there. But when we computed the numbers we found, we only expect around 0.2 a year because the area of the deep drilling fields is so small. Another way how we may be able to separate lensed and unlensed type 1a supernovae is by looking at their colors and magnitudes. So here in this plot, you see that you can see a bit of separation between the unlensed supernovae, which are the black points, and the lensed ones, which are the colored points, because lensed supernovae are brighter at the same redshift than unlensed supernovae. And this is just an additional clue that can help you to decide whether something is likely to be a lensed supernova or not. Then we also wanted to see whether we would already be able to infer a time delay if we use only data from LSST, because that's what we will get anyway. So for this, we fitted some simple templates to the light curves, and we saw for how many of the systems we could recover the accurate time delay. Well, the short answer is not many. So only a few % of the systems have time delays that are sort of usable. So this really builds the case that we need follow-up observations to do cosmology from lens supernovae. So we also looked at a subset of our sample that would be suitable for these follow-up observations. So we want systems that have large enough time delays, that are detected early enough, and also are bright enough for follow-up observations. And when we apply these cuts to our sample, we're still left with around 10 objects per year. And then if we assume some uncertainties in the mass model and the time delay, which of course will depend on the data quality and the system you get, but as a rough estimate, if we assume 5% errors, then we would be able to constrain the Hubble constant to 1.5% precision in only 3 years of LSST observations. This is really great. It's optimistic, but of course, this also, we can only reach this if we really have our classification and follow-up strategy completely nailed down. And that is something that we're working on at the moment. So both in the strong lensing science collaboration and also the strong lensing topical team within the dark energy science collaboration, we're working together to prepare for strong lensing science with LSST. And just to give you a bit of a flavor of what sort of activities this involves, there's a lot of different things, and so many people are working on this. So here I highlighted a few ones. So for simulations, we have SLSim, which is the strong lensing simulation pipeline. And SLSim can simulate a lens population of static lenses, but also variable lenses, and then inject them into data cutouts so that you get a catalog of realistic lens images. So here you see examples for Galaxy lenses and also time series of a lens supernova. And of course, you can get light curves as well. And SLSim is very flexible, so the user can input what you want, what sort of population you want, and what sort of data, so that everyone can use it for their own science case. Now, with these simulations, we can also do some search challenges. So now we're initiating a static lens search challenge and a transient lens search challenge. And the idea here is that everyone can test their lens finders on the simulations to see how it works, because we don't want to choose one method of lens finding, because every method will yield different objects. So we want to use all of them together. And for the transient side, the team that's leading this challenge is Jolteon, Gotta Catch Them All. So they're putting together a data set with a lot of lens transients, but also contamination. And then everyone can join the challenge. And the idea is to see how many lens transients we can recover together. So the spirit is collaborative and not competitive. So if you're interested either in joining the challenge or in helping them putting it together, then you can join the Slack channel over there. Okay, so then we have simulations, search challenges. We're also making forecasts for cosmology, and a lot of people are working on this also within Desk to combine it with other cosmology probes so that we really can see what the combined effect is of all the probes we have. For that, of course, we need follow-up resources as well, which we're also coordinating internally, and we're writing proposals to get more observations. And finally, when we have all the observations, we need to store it in a database. And for this, we have many different databases. So some are a bit more specific towards transients or galaxy clusters. Others are a bit more general. And they seem to be a bit inspired by cats, which is kind of cool. And another function of the databases is also to serve as a watch list. Because if we know which galaxies are known lenses and we see a transient going off there, then we can trigger follow-up observations. So that's another good use of them. Okay, so with all these efforts together, I think that the future for strongly lensed supernovae with the Rubin Observatory is looking very bright. So currently we have only discovered a handful of lensed supernovae, but Rubin will discover orders of magnitude more. So we predict around 44 lensed type 1a supernovae a year, not even counting all the other types of supernovae. And a subset of that will also be able to constrain the Hubble constant very precisely. But for this, we definitely need good search methods and follow-up, which is crucial. And then besides learning more about cosmology, we'll also learn a lot about lens galaxies, supernova physics, and who knows what more. So I think exciting times are ahead. Thank you.
Thank you. Are there questions for Nikki?
Hello, Nikki. Thank you for delighting us with your drawings.
Thank you.
Because you have these two populations of lens supernovae that have such different time scales in the time delay, what is the ideal cadence? What is the ideal return time for observations in LSST for your science?
Yeah, for our science, so, oh wait. Yeah, so we expect a mean time delay to be around 10, 15, 20 days. So something around that. And actually the cadence of LSST is not really high enough to then accurately measure the time delay on that time scale from LSST data alone. So this is why we did these tests and we need to supplement it with other observations. So for us, a bit more higher cadence would be better.
Hi, Nikki. It's Sherry speaking here. It's thanks for the great talk. So as you mentioned, follow-up is very important to get the time delays. So one quick question I have is, will there be, for example, resources from the in-kind contributions in terms of follow-up observations to help with monitoring some of these new lens systems from Rubin?
Yeah, we have some follow-up also for the lens modeling, so more high resolution. I'm not sure from the top of my mind if we also have follow-up to get better time delays. So LS4 will be there, which is very useful because that's another survey telescope that will run simultaneously with LSST. But I don't think that's an in-kind contribution. But maybe other people know more. But hopefully we can, in some way at least, merge the two and have better light curves.
All right, let's thank Nikki again. And thank you to all of our speakers in this session.